Hello, and welcome to week number 4, AB Calculus. My name is Mr. Shanklin. Let's get going. Let's review a little bit about last week. Last week we were talking about functions that are continuous, functions that are discontinuous. How do you find if a function is continuous or not? In this problem right here, it says that f of x is equal to x squared minus x over 2x when x does not equal 0. Why do they say when x does not equal 0? Well, because if you factored the top, okay, and that's usually when you have problems, is when you factor the top and the bottom and nothing. Hi, Isabel, how are you doing today? I thought I was going to end up doing this all by myself today. I'm doing well. Kind of bumming that I'm not outside today. I was outside all the way until like 12:30, and then it started raining, and it's like, oh no, I like to do all my classes outside because it's so much nicer. But that's beside the point. So, how's everything going so far? Is calculus easy so far? I think this week, I love this week. This week is this is the end of limits and continuous functions and all that, and then we start with the derivatives next week, which is a little bit tougher. But this week, I like the limits that we're doing this week. But in this problem, I'm just doing a couple review problems from last week. F is continuous at x equals 0, then k is equal to. Well, if you take a look at this function up here, the first thing I always do is I always try to factor things out. So if I factor out an x here, I end up with x minus 1, and I have 2x here. Well, right away I look at this and say, oh, something's going to cross off on the top and bottom, and x is going to cross out. Well, what makes this equal to 0? Well, when x equals 0, this function is undefined, or now I know that because it was on top and bottom, I know that at x equals 0, there is a hole in my graph. Now, the rest of the graph is just x minus 1 over 2. Well, what is x minus 1 over 2? Can't I rewrite that as 1/2 x minus 1/2? So really, this graph right here, x squared minus x over 2x, is the exact same graph as this, except at x equals 0, there's a hole. So this thing is going to look something like this, 1/2 x minus 1/2. So it starts down here, and then it comes up like this. But at x equals 0, there is a hole in my graph. So the hole is right about there. They want me to fill in the hole. Well, just by looking at the answers, I know that it's not this, it's not this, it's not this. Just by looking at my graph, it's got to be either -1/2 or -1, because I know it's below the x-axis. So then how do I fill it in? Well, all I have to do is plug 0 in here. 0 minus 1 is -1 over 2. That would fill in. If k is equal to -1/2, that would fill in this hole, and it would make this a continuous function. Okay, so last week really dealt with a lot of factoring. So a problem like this, it says find the intervals in which each function is continuous. Well, functions, the first thing you want to do when you have problems like this is you want to factor. So here I have x squared minus x minus 12. I'm going to factor this thing down. So this becomes x minus 4, x plus 3 over x plus 3. Well, the x plus 3 on top and bottom are going to cross off. So I know that at x equals -3, because that's what makes this equal to 0, so at x equals -3, there's a hole in the graph. So that function is going to be continuous everywhere except at x equals -3, because there's a hole in the graph. Now this second problem here looks like it's going to be about the same thing. So I'm going to go, let's see, what would that be? X minus 3, x plus 2. I ran out of room. X plus 2 down here. So those x plus 2s are going to cross off. So that means that x equals -2, there's a hole in my graph. Okay. Now this one's going to be a little bit different. There's not going to be a hole in the graph. I don't think there's going to be a hole in the graph. I've got x squared plus x plus 1. does it factor? This thing does not factor. I shouldn't say that. I don't see where it would factor. I don't think it factors over x plus 1. So it's kind of a weird problem that it doesn't factor, because then it's like, okay, what does the graph look like? I have no idea what the graph looks like, but I have a feeling it looks something like this. But I'm not exactly sure where this is equal to 0. I would assume that's going to be an imaginary number. That's a bad problem. We'll cross that one out. But now, let's say I gave you something like this. I'm going to flip one of these things over. I'm going to flip this one over. I'm going to say, what if I gave you a problem like x plus 3 over x squared minus x minus 12? Well, again, I would factor. The top doesn't factor, but the bottom does. The bottom factors to x minus 4x plus 3. Well, the x plus 3's will cross off, so I know there's a hole at x equals negative 3. However, this doesn't cross off, and it's still in the denominator. So whatever makes that equal to 0, well, x equals 4 makes that equal to 0. There's a vertical asymptote. So I know there's a vertical asymptote there. So factoring is a huge skill that students of calculus need to have, because it really does help when you can factor. All right, this week we're going to find limits and horizontal asymptotes and vertical asymptotes. Okay, I think it's fairly easy. I think most kids will do a nice job on this. But remember, after you're done, there is a final assessment for Chapter 1, which kind of just puts all the stuff together. What you will be learning about today, we're going to be connecting infinite limits and vertical asymptotes. We're going to connect limits at infinity and horizontal asymptotes. And we're going to be working with the intermediate value theorem also. Limits and infinity. All right, I got a short little video here. I'm going to make sure I do the right one. All right, 1 second here. I've got to share this application screen. All right, and that's intermediate value theorem, limits and infinity. Okay, let's take a look at this one. Let's see what it says.
We'll delve into the mysterious and ancient relationship that exists between limits and infinity. As you calculate various values of f and evaluate different functions, you can come across some bizarre things. For example, take a look at this function. F of x equals the fraction 2x plus 1 divided by the quantity x minus 3. Now, if you plug in 3 to this, you're going to get 7 divided by 0. Now, I know we've seen 0 divided by 0 in a lot of previous examples, but we've never seen a non-zero number divided by 0. Well, that's bizarre, I know, and it indicates something important. In fact, whenever you substitute a number into a function and get a non-zero number divided by 0, it indicates the presence of a vertical asymptote. And this holds true for this function. Let's take a look at the graph of f at x equals 3. Well, remember, an asymptote is a line which a function cannot reach. Here we have an asymptote at x equals 3 because when we plug 3 into f, we got a constant divided by 0. Now, by examining the graph of f, we can see that the limits as x approaches 3 from the left and right are different. As you approach 3 from the right, f gets infinitely large, so we can say that the limit as x approaches 3 from the right of x is infinity. However, as you approach 3 from the left, f of x gets infinitely negative, so we say the limit as x approaches 3 from the left of x is negative infinity. Vertical asymptotes aren't the only asymptotes related to infinity. Horizontal asymptotes do as well, just in a slightly different way. To see this, let's look at the graph of f again. Now, as x gets infinitely large, or as we go along the x-axis, note that the graph of f is bending slowly downwards towards the height of 2. Now, if a graphical argument is not enough for you, take a look at this chart based on the function values of f. As x gets larger, f gets closer to 2. Now, mathematically, this means that the limit as x approaches infinity of f equals 2. By the way, the limit as x approaches negative infinity of f also equals 2. As we travel left along the x-axis, the function approaches the same height. When I was explaining the last example, I said that x was getting infinitely large, and we translate that mathematically as the limit as x approaches infinity. Now this type of limit is called a limit at infinity. If this limit exists for a function, then that function possesses a horizontal asymptote at the height given by the limit. That's a lot of gobbledygook, but it's very simple in practice. Limits at infinity are very easy to calculate. All you have to do is compare the degrees in the numerator and denominator of the given function. By the way, the degree is the highest exponent. So if we take a look at f again, we'll notice that the highest degree in both the numerator and denominator is 1. Because remember, we don't write power, it's inferred to be 1. Now in this case, the degrees of both the top and bottom of the fraction are equal. And therefore, the limit at infinity of this fraction is going to simply be the coefficient attached to those highest degrees. Again, sounds like a lot of gobbledygook. We just take the coefficients of those x terms to make up the limit. Therefore, the limit will be 2 over 1. And we say that the limit as x approaches infinity of 2x plus 1 divided by x minus 3 is 2. And remember, we already know from the graph of f that the horizontal asymptote is 2, so it checks out. Now what happens if these degrees are unequal on the top and bottom of the fraction? Well, if the denominator's degree is higher, then the limit is 0. But if the numerator's degree is higher, the limit doesn't exist because it's infinity. In conclusion, if the limit as x approaches c of f of x is infinity or negative infinity, then f has a vertical asymptote at x equals c. Whereas, if the limit as x approaches infinity of f of x equals z, then f has a horizontal asymptote at y equals z. One word of caution. When we say that a limit equals infinity, we're actually saying that limit technically does not exist, because limits have to be a real number. Therefore, it might be more enlightening to say that the limit does not exist because it increases infinitely, rather than saying that the limit equals infinity.
Grammarly.
All right. That was a lot, but that is the whole gist of this week, is trying to find limits as things go to infinity, or if it's a vertical asymptote. Okay, so the definition in our textbook, it says connecting limits at infinity and horizontal asymptotes. The definition of a horizontal asymptote is if the limit as x approaches infinity is a number, then that number is a horizontal asymptote. And an example of that is right here. If I gave you this function x plus 1 over x, and I had you graph it out, this is what the graph looks like. Okay, and if I drew in a horizontal asymptote there, so the graph looks like this. If I drew in an asymptote at 1, my graph is not too straight. That function is, as it goes as far to the left, okay, because this is negative infinity out here. This is positive infinity out here. So as I go closer and closer and closer to negative infinity, my function gets closer and closer to this asymptote, which is just 1. How do I know it's 1? Because if I asked you what the limit as x approaches infinity of x plus 1 over x, all we do whenever we're trying to find a limit as x approaches infinity is we take a look at the highest power on top and bottom. This problem, the highest power on top and bottom is 1. So then I just look at the coefficients. So it's 1 over 1 or 1. So the limit is just 1. Easiest way to find a limit when you're looking at problems like that. So the limit is just, you just look at the highest power on top and bottom. Now let's say I gave you problems that the powers aren't the same on top and bottom. Okay, so let's say I said, okay, what is the limit? I got to turn my marker back on. Let's see here. All right, so if I said, what is the limit as x approaches infinity of x squared, let's go 3x squared plus 4x plus 5 all over 3 plus x. What is the limit there? Okay, What is the limit? This is one of your questions today. X squared is the limit. The limit cannot be a variable. The limit has to be a number. Okay? Has to be a number. The limit is 1. I'm going to disagree with that also. Okay? Now, and he went through it kind of quickly. We're going to look at the highest power on top and bottom. Okay? The highest power on top is x squared, right? The highest power on bottom is 1. Okay? So we have what is called a big over small. This is bigger, this is smaller. So if you're finding a limit as x approaches infinity of a larger over a smaller, we say that the limit goes to infinity. Okay, it's going to go up. If you graph this function out, okay, and I just made this thing up. I don't even know what the graph looks like. So let's get Desmos out, because Desmos is my friend. So I'm gonna write down this function, because I know as soon as I go to Desmos, I'll forget what it is. Okay, so what I'm saying is, as the limit as x approaches infinity, I'm saying that the answer is infinity. I'm saying I don't know what the rest of this graph looks like. I have no clue. But what I'm saying is, at the very end, this graph is going to shoot up. Okay, that's all I know with this limit, because it's a big power on top, small power on bottom. So let's check this out. Let's see if Mr. Shanklin is correct. Okay, and sometimes I'm not correct. Okay, sometimes I make mistakes, but I'm thinking big over small is infinity. Okay, so here's my, I probably didn't share this with you, so you probably can't see that. Okay, so we're going to share that. I guess it's not sharing. Let's try this again. Go Chrome tab, Desmos calculator, share. Okay, so now you should be able to see my calculator. No, still not. Okay, here we go. Okay, so now I'm going to put in my function. I'm going to put in, okay, I got to read what I have, 3x squared plus 4x. So 3x squared plus 4x, all divided by, oops, I want to do that. I should have put this inside parentheses, that way I will see if I can put this inside parentheses. So, and then now the whole thing is divided by 3 plus x. Okay. So I did not know what the graph looked like, but now take a look. As it gets farther and farther out here toward infinity, look what the graph is doing. It's going up, 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 up. So, in conclusion, if you are finding a limit as x goes to infinity, all you're going to do is you're going to look at the highest power on top and bottom. If the highest power on top, okay, so I'll write this out again. If the highest power on top, if it's big over small, so the top one is bigger than the bottom one, your limit is infinity. If I give you a problem like this, let's say I gave you the limit as x approaches infinity of 3x squared plus 4x plus 5 all over 7x to the third minus 2x plus 2. Okay, now I look at the highest power. Well, the highest power on top is 2. The highest power on bottom is 3. So the bottom is bigger than the top. So I've got a small over big. If you ever have a smaller function on top, big on bottom, it's going to be 0. The limit is going to be 0. I don't know what the graph is going to look like. I don't know what this graph is going to look like. It could look something like this, but I do know that it's going to end up being the end behavior is going to go toward 0 at the very end. Now you can get Desmos calculator out, you can plug this in, and you will see that at the very end of this graph, the farther you go to the right, it's going to go to 0. Okay? And then if the last one, so we've got big over small, small over big, Okay, so here we go. I'm going to write these down. These are very important. So if you have the limit as x approaches infinity, and if you have big over small, your limit is infinity. If you have the limit as x approaches infinity, and you have small over big, your limit is going to be 0. If you have the limit as x approaches infinity, and they're the same, okay? The power on top and power on bottom are the same, then you have to take the coefficient. So if I had something like 3x squared plus 5x over 7x squared minus 2, the powers are the same, so I take the coefficients. So the limit would be 3/7. That's the only way these things can happen. You can either have the powers are going to be the same, or the power on top is going to be bigger than the power on the bottom, or the power on top is going to be smaller than the one on the bottom. Those are the only ways it can happen. Okay? Does that make sense? Okay, before we go into some problems. Okay, so let's try a couple examples. All right, what is my answer for the first problem? Okay, I've got the limit as x approaches infinity of 4 minus x squared over x squared minus 1. What is my limit? -1. I would agree. It is -1. How about number 2? I have the limit as x approaches infinity of 4 minus x squared over 4x squared minus x minus 2. -1/4. Yeah, these are pretty easy once you have the hang of them. How about this one? Now remember, this one it says the limit as x approaches negative infinity. So you're really just putting a negative in place of it. So see what you get for an answer. Well, I don't think it's going to matter. I guess it does in this one. Negative infinity is correct, right? Because you have a big over a small, but it's going to negative infinity, so that function is going to negative infinity. I agree. How about the next one? 3x squared plus 27 over x to the third minus 27. 0 is correct. See, when you get the hang of these, they are super easy. All right. How about this one's a little bit trickier. The limit as x approaches infinity of 2 to the negative x over 2 to the x. You're stuck. Okay, I'm going to rewrite this problem. Okay, I know that a negative x, I could rewrite this as 1 over 2 to the x times 2 to the x, couldn't I? Because what does a negative exponent do? It just brings it down to the bottom. So this is really 1 over 2. Now I'm messing up because if the exponents are the same, you just, I'll just leave it as this. If you think about the limit, what is this number going to go to? If x gets bigger and bigger and bigger, so I start putting large numbers in here, what does this number go to? Like if you have 1 over 10, 1 over 100, 1 over 1,000, 1 over 10,000, what does this number start heading toward? Because that's what a limit is. So what is this function going to? The fractions get smaller, right? What is 1 over 10 is 0.1. 1 over 100 is 0.01. Oops. 1 over 1,000 is 0.001. 1 over 10,000 is 0.00001. So where is this going to? The larger it's going, it's getting closer and closer to 0. So the limit of this problem is just 0. Because I've got a small number on top, I've got a big number on bottom, and that is going to be 0 on there. All right. The next one's a little tricky, not as hard as the first one, but it's a little tricky. What do you think that answer is? Two? All right. Now, is it 2 or is it -2? First thing I would do is I would multiply this thing out. So I've got 2 minus x times 2 plus x. So if I multiply this out, I end up with 4 plus 2x minus 2x minus x squared. I don't care about any of this stuff. All I care about is this one. So I end up with 2x squared on top, negative x squared on bottom. I'm going with -2. Okay? So yes, it should be -2 there. So some of these can get a little tricky, but the concept's always the same. You're looking at big over small, small over big, or the same on top and bottom. This graph you should have memorized. I think week number 2 I told, or maybe week number 1 I said to memorize this graph. Let's see here. All right. If you have this graph memorized, then you would know that the limit as x approaches infinity of sine of x over x equals 0, and the limit as x approaches negative infinity of sine of x over x equals 0. And that is the reason this graph, because this graph looks like this. It goes up to 1, and then it does the same thing. Okay? So the farther out you go to positive infinity, this function is getting closer and closer to 0. Same thing here. Now this is the one problem that really had me messed up when I first started doing calculus, because it's like I learned that a horizontal asymptote, an asymptote means that a function gets closer and closer and closer. If you think about this graph, the horizontal asymptote for this graph is 0. Okay, the horizontal asymptote. But look at this graph crosses that asymptote over and over and over and over again. But it's still an asymptote. The function isn't getting closer and closer to it. It is getting closer and closer to it as it gets out, but it's crossing it all the time. So that kind of messed up my whole philosophy on what is an asymptote, because I was always taught an asymptote, a function gets closer and closer to the asymptote, but it never hits it. Well, this function disagrees with that, because this function crosses that asymptote hundreds and hundreds of times as it goes out to 0. So it's an interesting graph. But if you know that graph, because they'll throw a problem like this on an AP test, and it's like, oh no. But if you know the graph, it's like, oh, that's easy. I know what the limit is as it goes that way out there, because it has to be 0. Okay, now, vertical asymptotes. Vertical asymptotes, when you have a problem like, let's say, 5 over x minus 2, and I asked you to graph this out. Well, I know that anything that makes the denominator equal to 0 is a vertical asymptote. So here I have x minus 2, so I know that at positive 2, there is a vertical asymptote. Now, I don't know what the graph of this looks like, but I've done enough of these problems that I know that, and I could just graph 1 or 2 points, but this graph is going to look something like this. How do I know that the x-axis is an asymptote? How do I know that? Because did you see how I graphed that thing out? I graphed it, and as soon as I got to the x-axis, I kind of curved it. Why do I know that? Well, because if I did the limit as x approaches infinity of this, I've got a small over a large, right? Because this is a constant. This number is getting bigger and bigger and bigger, right? If you put infinity in here, you've got 5 over infinity. This is basically 0. So I know that 0, because remember, when you have a limit as x approaches infinity, if it turns out to be a number, that number is a horizontal asymptote. So I know that this has to be a horizontal asymptote right here. X equals 0. That has to be a horizontal asymptote. So now, if I asked you what is the limit as x approaches 2 from the right, and what is the limit as x approaches 2 from the left, what would you say? Let's go with the first one. The limit as x approaches 2 from the right-hand side. Positive infinity. What is the limit as x approaches 2 from the left-hand side? Then here's the question of the day. What is the limit as x approaches 2? Does not exist exactly, because the limit from the left and the limit from the right are not the same. If they're not the same, the limit does not exist. Woo-woo! You got it. Awesome. So let's try a couple examples of those. So if I gave you this problem right here, okay, f of x equals 8 over 4 minus x squared. Okay. If I was going to find out, what's happening here, there's a lot happening, because if I factor the bottom, oops, turn my marker on again. So if I factor the bottom, I end up with 8 over 2 minus x, 2 plus x. So I know at 2 there's a vertical asymptote at 2 and positive 2. So at 2, negative 2, and positive 2, there's a vertical asymptote. And I know there's a horizontal asymptote at 0. Why do I know that? Because it's a big number over a small number. Big over small, 0. So I know that there's a horizontal asymptote here. So right away, wouldn't have this been cool if you knew this stuff like in pre-calc? Because now, I don't know who your pre-calc teacher was, or if you had pre-calc, because now you can graph all these crazy functions. Just knowing what the vertical and horizontal asymptotes are, super easy to graph these now. And then looking at the graph, you should be able to figure out what all of the limits are as it comes from the right-hand side, as it comes from the left-hand side. So those are some cool problems. I like those. All right, so in this problem, I'm going to let you work on this one by yourself. It says the graph of f of x equals 4 over x squared minus 1 has one vertical asymptote at x equals 1. The y-axis is a vertical asymptote. The x-axis is a horizontal asymptote, and x equals plus or minus as vertical asymptotes. What would your answer be there? Letter C. I agree with you. And the reason I agree, okay, if I'm going to do this problem, the first thing I always do is I always try to find the horizontal asymptote. Why do I do that? It's the easiest thing to do in the world. The limit as x approaches infinity of 4 over x squared minus 1. This is a very big number. This is a very small number. So I have small over big. That is 0. I know that y is equal to 0 is a horizontal asymptote. That is a horizontal asymptote. Then, to find the vertical asymptotes, I just factor the bottom. X minus 1, x plus 1, over 4. Nothing crosses off. So I know that x equals 1 and x equals negative 1. Those are vertical asymptotes. And that's exactly what letter C said. The x-axis is a horizontal asymptote because the x-axis is y is equal to 0. And the two vertical asymptotes. Very nice. All right. This is a tough one. All right, so I'm going to turn off my mic. I'm going to let you work, see what you get there. Oops, I'm talking and I don't have my mic on. Letter C. Okay, I have not done this problem yet, so I'm not 100% sure. But the first thing I would do on this is I'm looking at the horizontal asymptote. Horizontal asymptote, easiest thing to find. The powers are the same on top and bottom, so I know that at x equals, or I'm sorry, y equals 1/2 is a horizontal asymptote. Okay, now in order to find vertical asymptotes, I have to factor this thing. Factoring, I'm going to pull out a 4x on the bottom. So that leaves me with x minus 1. And then I'm going to factor the top. I don't know if the top factors or not. So I'm going to try to do this really quick. I'm using the cheater method. So if I multiply through here, that gives me 6. What two numbers multiply to give me 6, but add up to 2? Yeah, top does not factor. So it does not factor. So that means 0 and 1 are vertical asymptotes. 0, 1 vertical asymptotes. Horizontal asymptote is y is equal to 1/2. 2 vertical asymptotes, x equals 0, x equals 1. That's absolutely correct. C is the correct answer there. Very nice. Excellent. That's why I said factoring is such a huge skill in calculus. You have to be able to factor all the time. All right, now we're going to talk, the last thing we're going to talk about today is called the intermediate value theorem for continuous functions. Let me give you the mathematical definition here. A function y is equal to f of x that is continuous on a closed interval a to b takes on every value between f of a and f of b. In other words, if y sub 0 is between f of a and f of b, then y sub 0 equals f of c for some c in a and b. All right, let me show you a example that will make this a lot clearer. All right, so let me turn this on. Gotta find it. All right, and let's make this larger. The intermediate value theorem.
For a function to be continuous, we can look at our first major continuity theorem, the intermediate value theorem. Now, before we get into explaining what it means, let's take a look at exactly what it says. If f of x is a continuous function on the closed interval ab, then for every d we pick between f of a and f of b, there exists a c between a and b such that f of c equals d. Whew, that's a little complicated. But it's not so difficult if you take a look at what it means visually. We'll begin with a function f, which is continuous on the interval ab. In other words, the left endpoint is a and the right endpoint is b. Therefore, this height must be f of a, and this height must be f of b. Now let's pick some height in between those two, any one at all. I'll pick this one, and we'll call this height d. Now the only thing the intermediate value theorem is saying is that this value, or height, d, is going to cross our function at least once. Not only will it cross the function, it will cross the function between the x values of a and b. As you can see, it crosses the function right here, and we call that x value c. See how this ties in with the theorem? If we pick a d between f of a and f of b, then it relates to a c between a and b. That's it. That's all there is to the intermediate value theorem. If you don't quite understand it, well, let's take a look at a real-life example, and it'll become even clearer. As promised, here's a real-life example of the intermediate value theorem. On a website called thespark.com, they held a contest called the Fat Project. You've probably seen posters and billboards that say, lose 30 pounds in 30 days. Well, the Fat Project was an exercise to see if someone could gain 30 pounds in 30 days. They really tried hard. Here's one of the participants in that project. Her name is Nicole. On October 1st, she weighed 121.5 pounds, and her goal by October 31st was to reach 151.5 pounds. Here's her weight gain graph over that time period. I think you'd have to agree, it's pretty impressive. So let's take a look at the intermediate value theorem with this graph. As you can tell, on October 2nd, she'd already gained 6 pounds. That's only one day into the contest. Huzzah for Nicole. However, on October 28th, she had gained 22 pounds. Well, according to the intermediate value theorem, I should be able to pick any value between 6 and 22 pounds. we'll say 14 pounds. And I know that Nicole must have gained 14 pounds at some point on the graph between the 2nd and the 28th. Now think about it again. It makes perfect logical sense. If your weight on day 2 is 6 pounds heavier than you started, and on day 28 is 22 pounds heavier than you started, and at some point in between there, you had to have weighed 14 pounds more than when you started.
If you want to eat healthy and feel your best, you gotta try Ka'Chava. Ka'Chava is the world's healthiest all-in-one meal shake.
All right, so that is the intermediate value theorem. Now, the intermediate value theorem, it comes up all the time on the AP test. You know, when they ask you, why is this true? A lot of times it's just the intermediate value theorem says so. What type of problems would they have you do? This is a type of problem that they would ask you to do. It says find the value of C guaranteed by the intermediate value theorem. So in this problem, I have an interval of 1, 5. So I'm going to just plug in f of 1. So f of 1 is equal to, and if I plug 1 in here, 1 squared is 1 minus 1 plus 9. That's equal to 9. And then I'm going to plug 5 in there. So f of 5, and then if I put 5 in there, that gives me 25 minus 5 plus 9, so that's 29. So the intermediate value theorem says that there has to be some value between 9 and 29 that f of C is equal to 11. Now, I'm supposed to find that value. I know it can't be 1, right? Because that's 9. I know it can't be 5, so it's got to be one of these. I could do it algebraically. I could just go x squared minus x plus 9 is equal to 11. And I could just solve for x. So x squared minus x minus 2 is equal to 0. And if I factor this, I get x minus 2. Is that right? Yeah, and x plus 1. So my values are 2 and negative 1. Well, it can't be negative 1 because that's not in my interval. So it has to be 2. Has to be the correct answer there. That is the intermediate value theorem. I love that FAT project because it makes so much sense. You know, if you weigh, you know, in between there, you have some point in there you have to avoid, you know, the 100 and whatever it was. So that is the intermediate value theorem. When in doubt, if you're taking an AP test and it asks you why is this true, a lot of times you just write down intermediate value theorem, and it's just IVT. That's just stands for intermediate value theorem. Whew, that is all I have for today. Any questions on any of this stuff? Should be a fairly easy week. Sure. Let's go to 2B. Let me erase this so I have someplace to write. Okay, I have to go into your assessment though. 1 second here. All right. Number 3, parts 3 and 4. Okay, so let me just jump into that. So that's week 2, 2B. All right, so let's see here. So that's 2B, number 3. Okay, number 3. Oh, oh, okay. I'll stop there.